All right, good morning, everyone. On behalf of myself, Steve, Ann, and Ryan, we're proud to present our senior design project titled Export of Marcellus Shale Liquefied Natural Gas. I'm going to start by giving a brief background and motivation for our project. Then Stephen will discuss some of the design challenges we faced. Ann will then talk about the technical approach and results. And Ryan will finish up with a costing and economic analysis and conclusion. Okay. So first, let's talk about natural gas, specifically natural gas that's produced from shale rock formations, known as shale gas. Shale gas is the biggest U.S. energy revolution since the Arab oil embargo. You can see here that shale gas has gone from 1% to 25% of all U.S. natural gas reserves in the past decade. It's estimated that there's a 100-year supply of 2,500 trillion cubic feet of natural gas in these shale formations. And these have been able to be accessed in recent years through advances in technology such as hydraulic fracturing, known as fracking. This has allowed the U.S. to become the #1 natural gas producer in the entire world. In 2012, the U.S. completed 10 times more wells than the entire rest of the world combined. This graph shows how the landscape of the U.S. natural gas production is changing. All other sources of natural gas besides shale has actually been decreasing and is expected to remain constant in the foreseeable future. However, shale gas is really leading this revolution and is providing an abundance of natural gas, and is expected to only increase as the future progresses. So we know that there's a lot of natural gas now being produced in the United States, but what are we going to do with this? And this graph shows the average natural gas prices around the world over time. The red line represents natural gas prices in the United States. You can see that this peaked in 2005 with the exploration and extraction of gas from these shale formations. This is in contrast to places around the world, such as Japan, which is represented by the orange line, where the price of natural gas has continued to increase in previous years. You can see here that this represents a large price difference, and we predict that this will continue in the near future, due in part to the abundance of natural gas present in the United States, as well as recent incidents such as the Fukushima accident. Taking this price difference, along with our estimated 2,500 trillion cubic feet of natural gas in shale formations, it's estimated that there's up to $25 trillion of value that could be unlocked if we were able to take natural gas at the lower U.S. prices and transport it to places where it's more expensive. So how exactly is natural gas transported? It's transported by being liquefied first. Liquefying natural gas reduces its volume by 600 times, which makes it economical to transport large distances by tanker. You can see that there are approximately 100 liquefaction facilities around the world. 3 are located in the United States. The diagram on the right actually represents the current import facilities of natural gas in the United States. So these are facilities that take liquid natural gas and vaporize it to natural gas for use. However, with the changing market for natural gas in the United States, 3 of these in the Gulf Coast are currently being retrofitted for export, as well as 1 located in Maryland, which we'll discuss further in our presentation. The global LNG demand is currently 250 million tons per annum of liquefied natural gas, and this is expected to double by 2030. So basically, the motivation for our project has become there's an abundance of natural gas being produced in the United States, there's a large price difference, and there's a large demand for it. So we want to be able to retrofit a facility that's capable of taking that and selling it to the global market. And with that, I'm now going to pass it off to Stephen, who's going to talk about some of the design challenges we faced.
Thanks, Ty. So, as Ty mentioned, the U.S. currently has many import facilities which are just sitting idle and not generating any revenue. Our goal is to improve the rate of return of new export LNG facilities. And we want to do this by retrofitting these existing import facilities rather than entirely new construction. So Cove Point and other import facilities are suited for retrofit because they have much of the existing infrastructure in place. Cove Point in particular is a good candidate because of its close proximity to the Marcellus Shale formation, which is leading the U.S. natural gas production. So our project scope is really to design this modular liquefaction process that can be applied to import facilities. This way, we can take these idle import facilities and turn them into revenue-generating export facilities. So here we have a diagram of natural gas from the wellsite production all the way to transport. And of these many steps, liquefaction is the most challenging and also the one that we'll be focusing on. is we'll be looking at Cove Point as a case study for this retrofit analysis. And as I mentioned, our goal really is to create this modular design that can be integrated seamlessly between the pretreatment and the storage steps. And with this seamless integration, we'll be able to take advantage of the import facility's existing pipelines and storage tanks. We estimate Cove Point to produce about 5 to 6 million tons per annum, which really isn't all that much compared to some of the world's largest LNG plants. But if we are only using one train, so if you look at the capacity per train, you can see that we really are pushing the envelope in terms of maximizing this capacity per train. And now I'll pass it off to Anne, who will walk us through some of the technical aspects of our design.
So in designing our liquefaction process, we started by looking at some of the existing LNG technology. And what we found was that we could remove some of the parts of these existing processes, such as liquid petroleum gas extraction and acid gas removal, in order to make our liquefaction process more modular so that we could fit it in between pretreatment and storage, as Steve mentioned. So the way our process is set up is we have natural gas coming from pretreatment into our process. It's liquefied, and then it leaves our process to the existing storage facilities that are already in place. In our process, we have 3 different types of streams interacting. We have natural gas, we have a propane refrigerant, and we have a mixed refrigerant, which consists of methane, ethane, propane, and nitrogen gas. The way you can see that our process can be divided into 3 different sections. First is the propane pre-cooling, where the natural gas comes in and is cooled from a warm vapor to a cold vapor. In the middle, we have the mixed refrigerant pre-cooling, where the mixed refrigerant leaving our main heat exchanger is cooled back down again before it re-enters that exchanger. And finally, we have our main cryogenic heat exchanger, where the natural gas is liquefied. So I'd like to walk through each of these in a little more detail, starting with the propane pre-cooling. And as you can see, this blue stream here on the left is our natural gas coming in from the pretreatment. So it comes in as a warm vapor, goes through a series of 3 heat exchangers, and then leaves as a cold vapor. In designing these heat exchangers, we first looked at using one heat exchanger as the most capital efficient solution, but we found that the most thermodynamically efficient solution was to use 3 heat exchangers, and this optimized and minimized our overall operating costs. We also wanted to get as much cooling capacity out of our propane refrigerant as possible, and so our choice of heat exchanger really helped with this. We chose to use kettle heat exchangers, which gave us the maximum heat exchange per unit area. And what the kettle exchangers also do for us is when the propane refrigerant is leaving each exchanger, it's split into 2 streams. We have the vaporized propane coming out of the top of each kettle, and that's sent back into a compressor and cooled again to be recycled into our cooling loop. And then the liquid propane leaving each exchanger, that still has a lot of cooling capacity. So we send that liquid refrigerant into the next heat exchanger to be used as the cool liquid. So now I'd like to talk about our mixed refrigerant pre-cooling process. And as you can see in the upper right here, we have the green dotted line, and that is the vaporized mixed refrigerant coming from our main heat exchanger. And at this point, this refrigerant has been warmed up a little bit because it's absorbed some of the heat from our natural gas while it's being liquefied. So this mixed refrigerant comes in and enters a series of compressors and intercoolers. And this repressurizes the stream before it enters a series of kettle exchangers that operate very similarly to the ones that we just looked at. So again, we're using propane refrigerant here to cool our mixed refrigerant. And the mixed refrigerant leaving the 3rd kettle exchanger is sent to a flash drum where it's separated into vapor and liquid mixed refrigerant streams that are sent to our main cryogenic heat exchanger, which I'll talk about next. So the main cryogenic heat exchanger is a highly proprietary piece of equipment, which makes it difficult for us to know how to model it. But we do need to model it in order to make the appropriate design choices. So our team found a way to model this in our Aspen Plus modeling software, and this enabled us to optimize our mixed refrigerant composition in order to maximize the efficiency of this part of our process, which makes up kind of the bulk of our utilities requirements. So the way that this heat exchanger is set up is it's like 2 spiral wound heat exchangers in one vessel. In the bottom half, we have what we call the warm bundle, and then in the top half, we have the cold bundle. We have 3 different streams entering through 3 separate tubes into this heat exchanger. We have, in blue, our natural gas stream coming in from our propane pre-cooling, and then we have the 2 mixed refrigerant streams that I just mentioned. So we first follow the liquid mixed refrigerant stream, which is the solid green line coming in from the right. The liquid mixed refrigerant rises up through the bottom half through the warm bundle, exits about halfway up our heat exchanger, and then is expanded and cooled through a turbine. And this also generates some power for our process that we can feed into the process. So this cooled stream, which is mostly liquid, is then sprayed down over the warm bundle, and that cools the components in the tubes that are rising up through that bundle. If we follow our vaporized mixed refrigerant stream, which is the dotted green line, this rises up through our warm bundle. Because of that spray, it's cooled and phase changes about halfway up our exchanger. Continues to rise up through the top. Like the first stream, it's expanded through a turbine and cooled and then sprayed down over the tubes rising up through. All of this mixed refrigerant kind of collects and leaves through the bottom back to the mixed refrigerant pre-cooling process that we just looked at. Finally, we have our natural gas stream as the blue dotted line coming in. It comes in as the cold vapor, rises up through the heat exchanger, phase changes to a liquid about halfway up, and then leaves at the top through a valve, is expanded and cooled to its final temperature of about negative 259 degrees Fahrenheit. At this point, it leaves our process, goes to some of these existing storage facilities, and then can be transported to global markets. Now I'd like to turn it over to Ryan, who will discuss some of our cost considerations and economic analysis.
Thanks, Anne. So in terms of costing, we're estimating that the total bare module cost of this process will be about $600 million. And that's simply the cost to purchase and install all the pieces of equipment required to run the liquefaction train, so compressors, pumps, heat exchangers. The important thing to note here is that one piece of equipment is really driving these costs, and that's our main cryogenic heat exchanger, which is the workhorse of any liquefaction process of this scale. We costed it as a function of how we modeled it in Aspen Plus as 2 shell and tube heat exchangers with an appropriate scaling factor to get at $500 million. So with these costs, we wanted to go ahead and build out a discounted cash flow model to look at the economics of this project, because it's really important here when we're looking at whether it's feasible to actually build this plant or not. So some of the base case assumptions that we assumed were the following: that it'll take about 5 years to get the process online, and that it'll produce for about 20 years with 6% downtime for maintenance. In terms of pricing, we're assuming that we'll purchase the feed gas at $5 per MMBTU and sell it to the Japanese liquefied natural gas market at $13. With these assumptions, we're looking at a net present value of about $219 million, an internal rate of return of 23.5%, and a break-even time period of 13 years, which we think is extremely attractive for a project of this size, which is likely going to cost a little over $1 billion in total to build. So with this model, we can actually start to look at certain variables and run sensitivities to see what's really driving the economics here. And here are 2 cases that we think are really interesting. The first is the differences in the economics between newly constructing a plant and retrofitting one. And so if we were going to build this plant from scratch, we think there'd be 2 changes to the assumptions we'd have to make. First, we'd have to increase our construction time by about 2 years, and then increase our total permanent investment by about 50%. The reason for this is that we'd have to purchase storage tanks, build pipelines, additional pieces of equipment that'll cost us more money. When we make those changes, our economics change drastically. So our internal rate of return drops by about 14.1%. And so the key conclusion here is that by retrofitting, you get another 14% annually on your return, which we think is a huge gain. Now the second thing we looked at was the price spread, which is simply the difference between what we're selling the LNG at to any international market minus the cost of the feed gas. The current market spread is about $13, but our model is indicating that the break-even spread, the point at which our IRR will go negative, is about $5. So there's a big cushion there. But the important point to note is that the price spread really drives the economics. So we want to take that risk off the table by signing a long-term power purchasing agreement to lock in those prices long-term. So to start to wrap up, we think there's 4 main conclusions from our project here. The first is that really retrofitting existing import facilities is a great way to boost the economics, increase your return, and extract a lot of value that's on the table here. Secondly, we found it really important to build a modular liquefaction process because that way you can use a lot of the existing equipment at these import facilities. The third point is that it's really important to optimize the composition of your mixed refrigerant, which is the refrigerant you're using to cool this natural gas to very low temperatures. This will increase your efficiency and reduce your operating costs. And fourth and finally, it's important to maximize the capacity of a liquefaction train. As Steve talked about earlier, we're really pushing that capacity with about 5 to 6 million tons of natural gas processed per year. And so we think these conclusions are pretty profound at a really important part in the energy industry in the United States, and we hope that these principles will be applied by companies in the next 5 to 10 years as they go and try and capture this value. Lastly, I'd like to conclude by thanking the following individuals. who helped us out a ton throughout the past year. Most notably, our faculty advisor, Dr. Holleran, Professor Fabiano, who's the head of the CBE design program, and then the chemical engineering industrial consultants who helped us out quite a lot. We couldn't have done it by ourselves. And with that, we'd love to answer any questions that you guys may have for our project.
Is that something that's like custom made for a project this big, or
We wish we could order it from Amazon. No, it's custom made for every liquefaction process. So certain companies will make less than 5 or 10 of them each year. You need to get the heat transfer coefficient to be extremely high. You really want to get the area to be as high as possible, so you work very closely with the engineers to build it, which is why it's so expensive, because it's custom made.
So what are the key differences versus the liquefaction technology that is being used in other facilities?
So I think what we try to do, a lot of the current liquefaction processes have, so I mentioned liquid petroleum gas extraction or LPG extraction, and that's built into the process. But some, I guess in some areas you don't need that necessarily. Like the Marcellus shale gas composition actually has very high proportions of methane and ethane and very low amounts of propane and butane and hardly any butane really. So we don't really need that in this part of the process. So we just wanted to take out anything that we didn't need and kind of narrow down to a very modular liquefaction process.
That's all we have time for.
Okay.
Thank you.
Thank you.